rational function notation, we were using r sub m comma n of z, where m denotes the degree of the numerator and n the degree of the denominator. Remember, a rational function, of course, being a ratio of polynomials. The terms of the partial fraction decomposition associated with a pole zeta sub I is called the singular part of our rational function around zeta sub I. So I told you a theorem on Friday, right, which was that every rational function where n is greater than m, that is to say the degree of the denominator is greater than the degree of the numerator, has a partial fraction decomposition. Okay, and the proof of this, we're not going to go through, but and why we're not going to go through it is because we haven't yet discussed Taylor expansions for complex functions. But it relies on constructing Taylor expansions for the difference of r sub n comma m comma n and the singular part of each pole individually, right? So essentially, here's an outline of how the proof goes. I'll just say in words, and then we may come back to this. It's not really important that you see the proof of this. It's more an algorithmic thing that you should know. That will help us a lot later. But the gist of the proof is that we can use the Taylor expansion to show that when we subtract the singular part of the partial fraction decomposition for each pole from r sub m comma n, we get the zero polynomial, basically by the balance on error that Taylor polynomials give us. Okay? So that's kind of the heart of it. But we're not going to go through that in full detail right now. And to be honest, I don't find it particularly interesting. I think we might all kind of believe that every rational function with complex variables where the denominator has greater degree than the numerator has a partial fraction decomposition. That's not to say it's not important that it's proven. I don't think it's necessarily a good use of class time. Okay, so with that being said, let's continue our investigation into the basic elementary functions of a complex variable, right? We've very briefly discussed polynomials. I've basically told you to treat them essentially like real polynomials. There is some difference. Again, we'll get back to that when we talk about Taylor series. Then we discuss rational functions. So we know we've already investigated quite a bit about the exponential function, complex exponential function. But I think it's worth revisiting because it's how we make a coherent definition of complex variable trigonometric functions. Okay, and you might be able to guess where that's going because the complex exponential function we express in polar forms in terms of real trigonometric functions. So this is kind of a guide as to how we will make a good definition of what it means to evaluate, for example, sine on a complex angle. There's no geometric intuition for what that means. But we should perhaps look to the real case and see if we can involve the complex exponential function somehow. And then maybe we'll have some guide. Okay, so first let me just recall. The complex exponential function is entire, right? Meaning that it's analytic on the entire plane, right? And satisfies d dz of e to the z is equal to e to the z. Much similar to the real case, right? Saw that before last week or perhaps 2 weeks ago. Okay. Which has polar components. Modulus of e to the z is just e to the x, right? And lowercase arg of z is just y plus 2k pi, where k is an integer, right? We have this multiple valued function which has infinitely many values. Remember back to our distinction between lowercase arg and uppercase arg. There's a reason that I say it this way, which will become clear soon. Of course, I didn't say here where z equals x plus iy, our standard convention. Okay, so even as a multiple valued function, which is not something we usually talk about, right? When we talk about functions, we typically mean something which is single valued. That is, it has exactly one output for any input that is acceptable. But we will soon see why it's important to consider multiple valued functions as separate entities and how that's useful to us. Yes?
Do you mean to write arg of e to the z?
Yes. Sorry. Thank you. Yeah. Good. Right. That's what I mean by polar components, right? I need the modulus and the argument. The polar components of the exponential function. Thank you. Okay. Good. So, from this description, we know, first of all, that e to the z is never 0, right? Because it always has modulus described by the standard real exponential function, right? And the real exponential function is never 0. It's always positive. Why this makes sense here, right? Say that a modulus is given by this function. Okay? So, however, assume all other complex values. Okay, so right away, this leads us to a key difference between the real exponential function and the complex exponential function. Right? The real exponential function is injective, or one-to-one. This is not so for the complex exponential function. So let's record that. Contrasting the real and exponential, the real and complex exponential functions for x1, x2 in R we know e to the x1 is equal to e to the x2 implies that x1 is equal to x2. That is, e to the x, or real x, or maybe I should say as a real function, is injective, or sometimes you'll also see the term one-to-one, which I have a slight preference against because it involves too many hyphens. Right, this is not so. For the complex exponential function, e to the z. Let's make a more precise statement, or maybe you can already guess at some values where e to the z fails to be injective. Anybody guess that?
Wouldn't it fail to be injected everywhere? Except, yeah, well, everywhere. You have to be.
What I mean to say is an example. Some pair of points in which it fails to be that specifically demonstrate that it's not injective.
I can do, let's see, z equals, well, not even points, but like, you could do at I, because you could every 2 pi as a big argument will result in the same complex number.
Okay, yeah, that's on the right track. Let's make the precise statement. Okay, so part A. E to the z equals 1. If and only if z is equal to 2k pi times I for k an integer, right? e to the z1 equals e to the z2 is the case if and only if z1 is equal to z2 plus 2k pi I. Or arbitrary integer k. So yeah, you essentially said this, right? If you add a multiple of
2 pi to the
2 pi
argument.
to the argument after you exponentiate, right? This is to say, the imaginary component of z2, then you get something that when exponentiated gives you the same value as z1. Okay? Okay, so, right. First, we'll just assume that e to the z equals 1, z equals to x plus iy. Right? So, this implies the modulus of e to the z equals e to the x is equal to 1, right? Of course, the complex number 1 has modulus 1. Okay? So this implies that x must be equal to 0. Okay? And so, in polar form, we have e to the z is just equal to 1 times cosine of y plus I sine of y is equal to 1, right? Which is the case if and only if cosine of y is equal to 1 and sine of y is equal to 0 simultaneously. So, what do we get? Y is just equal to some intermultiple of 2 pi. So, z is equal to 2k pi times I, right? Okay. Now, of course, the opposite direction, I'll just say easy check directly. Right? I just plug in any of these values for z, and I can verify the claim that e to the z will be equal to 1, given the polar form of e to the z. Right? I just didn't put other direction arrows on all of these, so I'll say this, check this directly. Okay? So, for B, let's start with what we said first as our assumption. E to the z1 is equal to e to the z2. Well, this is only the case. Remember, I told you that the usual rules of exponents apply here. So I can divide both sides by e to the z2. And get e to the z1 minus z2 is equal to 1. Right? By part A, tells me this is the case if and only if z1 minus z2 is equal to 2k pi I. Okay, so I just add z2 to both sides and I'm done. Right? Okay, this wasn't all too hard to prove, but it's something that will allow us to say much more about the rest of the basic elementary functions that we're going to be concerned with quite often. Namely, the trigonometric functions with complex input, and eventually what we get to today is the complex logarithm. Okay? So, but before that, let's say a little bit more about e to the z. Okay? It has some important properties that in the complex numbers that it doesn't have for the real numbers. Okay. Namely, for example, a function f is said to be periodic. In domain D, and here I mean domain in the topological sense, right? A open and connected subset of the complex plane, C. If there exists a non-zero constant lambda such that f of z plus lambda is equal to f of c. For all z in D. In this case, lambda is called a period. Of f. Okay, so that is to say, my theorem tells me that e to the z is periodic with periods 2 pi I, 4 pi I, 6 pi I, all the even multiples of pi I. Okay? In particular, we'll be concerned with the fact that it's periodic with period 2 pi I. Okay? It does have other periods, of course. Any integer multiple of 2 pi I will also be a period. But most often we'll be concerned with the smallest period. Okay? So as we've seen, e to the z, sorry, that looks kind of like a weird I. E to the z is periodic with period, and for emphasis I'll say for example, two pi I. Okay? So, what does this mean? This means we can divide the plane in to horizontal strips. As follows. Draw a picture here. Here are our real and imaginary coordinate axes, and I'll just have here's my point pi I, here's my point negative pi I, and take a strip here. Actually, it's misleading to put an arrow there, but let's just agree that these strips go on forever. Okay, I'll call this strip 0, right? And move up here. Say my imaginary axis continues up to 3 pi. This is strip 1. Likewise, I'll come down here. Negative 3 pi I. This will be strip negative 1. And the point is that I have this point z naught, or perhaps maybe let me just call it z, because I'm going to, the label, the index is actually what strip it's in. Z plus 2 pi I. Now here we have z plus, minus, oops, sorry, that's completely wrong. I'm supposed to be in this strip. Here I have z minus 2 pi I. Okay, so in general, this strip, these strips, each of them, S of n, are given by the following description. So we let x be anything, that is the real part of z, can be anything, and we restrict y between 2n minus 1 pi and 2n plus 1 pi. Okay, so what I'm drawing here, these points, these 3 points, and all their relatives in each strip for each integer. Well, I should say that too, where, of course, n is any integer. Okay, these 3 points and all their relatives up and down this vertical line produce the same value for e to the z. Right? So this is the visual description of what we wrote down algebraically before in the last theorem. Okay? So the important things to note here, e to the z will look the same in each strip, right? And furthermore, e to the z is injective on each strip. So, for these reasons, we call the SN, the SNs, fundamental regions for e to the z. Okay, so this is going to be thematic, right? Restricting the domain of e to the z to any one of these strips, S sub n, gives us an injective function. Why are injective functions important? Remember this from Calculus 1. Yeah, we can construct an inverse of an injective function, right? Because here's the graphical way to determine if something actually satisfies being a function. You draw a vertical line anywhere on the graph of the function. Does it pass the vertical line test? Does it hit the graph in only one place for any vertical line? So, dually, testing whether a function is injective for a function of one real variable amounts to the horizontal line test. For every horizontal line you can draw, does it hit the graph exactly once at maximum? No more than one time. If that's the case, then you can reflect it about the line y equals x and get a dead to rights function, something that passes the vertical line test. Right? Let me go. Sorry.
I've heard of not mixed any of this like force space with like the two inputs for a complex function and the two outputs, like a vertical cube test or something.
Yeah, so again, it's very hard to like come up with anything meaningful in terms of visualization for graphical interpretations of things. But just in case it wasn't clear what I was saying just now, let me draw you a quick pair of pictures.
Maybe I missed it in my Calc 1 class when I took it, but we define like an inverse to the sine function. The sine function fails horizontally.
Sure. But remember, in order to define an inverse for the sine function, you have to restrict the domain.
And have like the asymptotes.
Well, the inverse sine function doesn't have asymptotes, right? It just ends at a certain point. It's just defined in a...
Wouldn't this be periodic with the period y?
No, not for the inverse sine function. So you can define it for any section of the graph of sine that doesn't fail the horizontal line test. So, I mean, you could make some definition of notion of periodicity for like, oh, for these chunks you can define the inverse. But you're actually defining a different function each time, right? Because a function, the definition of a function depends on its domain as well.
So it's like, it has an inverse in each fundamental region sine.
Yeah, exactly, same thing here. We could choose any of these fundamental regions and construct an inverse for e to the z. And in fact, we'll do exactly that somewhat shortly. Okay? So, oh, right. Yeah, so here's the classic one variable example, something that you work with right away in calculus, right? Here's a function y equals x squared, right? Clearly this does not pass the horizontal line test. Any horizontal line I draw above the y-axis will cross the graph twice. So, but we still say that this function has an inverse because we choose where the x value is positive, right? And then when we flip around the line y equals x, that's what it means to take the inverse of something graphically, right? Because you interchange the roles of y and x. So you're reflecting about this line. Well, what do we get? Without restricting the domain, we get this, which is not a function. It fails the vertical line test, right? So we correct this by excluding this part of our domain, right? The negative x-axis, which would then give us just the top half of this parabola on its side, which does pass the vertical line test, right?
So when they tell us like way back in Algebra 1 that like root x is the inverse of x squared, it's not really the inverse, it's the inverse of x squared defined only for positive numbers.
That's right. That's why the square root of x is a positive number in Algebra 1, right? Because you're choosing, this amounts to the same type of choice that we made for the argument. We choose a principal value. Of course, it's a little more complicated for the argument because there are infinitely many possible values. For the square root function, there are two possible values. There's a historical precedent to be skewed more toward positive numbers. Maybe that's why we choose that as the principal value. But yeah, same type of idea. Yeah, good. Okay, so now as you might guess, when we try to define the inverse of a multi-value function, which is kind of a contradiction of terms, right? We're used to calling a function a thing that has a single output, right? Something that fails the vertical line test. Historically, in our careers, most likely, has not been allowed to be called a function. But for reasons which we will see increasingly throughout the term, we want to consider multiple value functions and consider their inverses. So, just as when we first encountered our first multiple value function, lowercase r of z, we made some choice, so will we do the same for anytime we take the inverse of a function which is not one-to-one. Okay? We'll make that more precise as the day progresses. Okay, so, but before we get there, let's just talk about trigonometric functions and how we can get there from our considerations about the exponential function, and kind of get for free practically that the trigonometric functions have many of their standard properties as they had when they were just considered as functions of a real variable. Okay, so now let's suppose we want to define trig functions for a complex variable. And we'll start with sine and cosine, right? Because if we define those in the correct way, then we can just rely on the old definitions to construct the new ones. Or not the new ones, sorry, the other standard trigonometric functions. Tangent, secant, cosecant, cotangent, etc. Okay, purely imaginary number, right? When we exponentiate that, we get a complex number of modulus 1, right? Because if we're purely imaginary, our real part's 0, and our modulus of the exponentiation of that is e to the 0, which is just 1. Okay, so in polar form, we write this as cosine of y plus I sine y. And if we look at the conjugate of that purely imaginary number and then exponentiate it, what do we get? We get cosine of negative y plus I times sine of negative y. Now, remember, cosine is an even function, which means that if we negate what we put into a cosine, it's the same as putting in just the thing without the negation in the cosine. Right? We can eliminate a negative sign inside a cosine. Okay? So, cosine of y. And remember also that sine is an odd function. The somehow opposite property of that cosine property holds. We can pull a negative out of a sine. So I'll pull this negative out just to get minus I sine of y. Okay? Okay, so let's add these together. What do we get if we add them together? We get 2 times, oh wait, no, I'm sorry. No, not a 2 on this side. We get e to the iy plus e to the negative iy is just equal to 2 cosine y, or said another way, cosine y is equal to e to the iy plus e to the negative iy divided by 2. And subtracting, e to the iy minus e to the negative iy is equal to 2I sine y tells us sine of y is equal to e to the iy minus e to the negative iy divided by 2I. Okay, so maybe, I remember the first time I encountered these pair of formulae was in a physics class. So maybe, I know we have some people studying physics in here, maybe you've seen this before. Especially if you've solved, I think like damped harmonic oscillator relies on this type of formulation of sine and cosine, right? Or not relies on, but it's easier to solve this way or something like that. Yeah, there's some business about this when you talk about damped harmonic oscillators, is what I vaguely remember also. But okay, so the idea is that this is a general formula for computing sine and cosine using the complex exponential function for just a real input of sine and cosine, or cosine and sine as I wrote here. So the idea is that, well, since we already are dealing with complex numbers in these two formulae, maybe we should just try to make this the definition of what it means to take the sine or cosine of a complex number. Okay? This suggests we should take this as a complex definition. And we'll shortly see that this is the right choice. And this makes sine and cosine of z of a complex number satisfy the same differential equations that sine and cosine satisfy for real input.
Just like looking at the form of those guys, they're very similar to like the hyperbolic trigonometric functions. More generally, like you could take like the hyperbolic cosine of iy, and you would get like the cosine of y.
Yep.
And is that like a property?
Yep. I mean, yeah, you just demonstrated it, right?
Yeah.
Yeah, so that's part of the beauty of these two formulae, is that it shows you the direct connection between the hyperbolic trigonometric functions and the standard trigonometric functions. It's all about a multiple of I in what you put into it. There's a lot of talk about this in the textbook. I decided not to say much about it because we won't have much occasion to talk about hyperbolic trigonometric functions. But maybe I'll include that on some future homework. Obviously, by the way, I've been working on making a good set of problems that will be released this afternoon. I'm still trying to whittle it down a little, just because there's a lot of things I think are interesting, but I don't want to make you have to work too hard for the exam, especially next Friday. But yeah, needless to say, I will release that this afternoon. I'll make some final decisions after class today. But yeah, maybe sometime in the future we'll say more about hyperbolic trigonometric functions, if people are interested. You know, we're getting close, even though we're like halfway through the term, we're getting close to, I see in our future that we'll be able to do some additional things. You know, we will have covered all the things that are required to be covered in a complex analysis course in general, a couple of weeks before the term actually ends. So maybe I'll have a poll later in the term as well as to what topics we should cover, what people are interested in, that we could talk about in more depth. But yeah, good observation nonetheless, that these equations highlight that hyperbolic trig functions and standard trig functions are intimately related. Okay? But in any case, let's proceed for now with our basic investigation. Okay, so now let's say for z a complex number, we let exactly these equations hold, but now with z instead of y. Sine of z is equal to e to the iz minus e to the negative iz divided by 2i. And cosine of z is equal to e to the iz plus e to the negative iz divided by 2. Okay? So you can verify right away that when you take the derivative of sine of z, what do you get? Yeah. Did you actually compute that, or did you just go by intuition?
You bring the I down, cancel the I in the denominator, you get plus.
Yeah. Yep. Good. Right. constant comes out, right? The derivative of e to the iz is just I times e to the iz minus the derivative of e to the negative iz is just negative I times e to the negative iz. Right, our negatives cancel here, we factor out an I. So we get e to the iz plus e to the negative iz, all divided by 2, or cosine z. And entirely similarly, exactly what we would expect in just based on the real case, right? Okay. So let me just say, additionally, many trig identities are recovered by this definition. Just for example, the complex function cosine of z is periodic with period 2 pi. What else can we say? All basic things. Our favorite old-fashioned trigonometric identity, the Pythagorean theorem in disguise. Angle sum and difference formulas. These are all recoverable, and who knows, maybe I'll ask you to do some of these, to recover some of these, and convince me that they're actually, yeah.
Are any not recovered?
That's also a great question. So, I think not. For anything that involves just sine and cosine, I think you're in the clear. Now it becomes a bit trickier when you try to translate things about tangent, cosecant, secant, and cotangent. Right, because I think that's mainly because the behavior around poles is more complicated for complex functions than it is for real functions. Okay. I actually don't know the answer to that directly, but I think there might be some difficulty, or it might be harder to show for some of the other trig functions. But good question. I don't know the answer off the top of my head. Okay. Now, what I will show you, what we will do together here, is an example which is not always the case for when we extend a real function into the complex numbers. But it does hold for sine and cosine. So let me tell you that sine of z is equal to 0 if and only if z is equal to k times pi, for k an integer. Okay? So that is to say, when we extend sine from the real numbers to the complex numbers, only the real zeros are the zeros of the complex extension. That's not always true or an arbitrary function that we extend to the complex numbers, you may well get many more zeros. But for sine, it works out nicely. Okay, so let's do this. Okay, so let's suppose sine of z, which just by definition is e to the iz minus e to the negative iz divided by 2I is equal to 0. Well, this implies that e to the iz is equal to e to the negative iz, right? And by our last theorem, what do we know about iz and negative iz if we know this equality?
It only happens if they're separated by 2 pi ki.
Yeah, that is to say the exponents, right?
Yeah.
Exactly.
Yeah.
By our previous theorem, this tells us that iz is equal to negative iz plus 2 times k pi I, right?
Yeah, because
2 times k pi I for some integer k, right? Add iz to both sides. So I get 2 iz is equal to 2k pi I, which is just the conclusion that I wanted. Z is equal to k pi. And I divide by 2I on both sides. Okay. Now, I made an if and only if statement. What's the justification for the other direction?
plug it in.
You just plug it in. And the equations I'm erasing right now tell you that this formula holds for real values as well. And so you can just plug it in and use that formula. Okay? That is to say, the formula is consistent with our usual definition of sine, right? For real numbers. Okay, so conversely, okay, that's something worth noting, I guess. You don't lose any zeros when you move to the complex numbers either. Sometimes you may gain some, but in this case, you don't gain any.
If you ever lose them.
No. As long as, yeah, so a good extension to the complex numbers will not lose any zeros, right? Because you want it to agree with the function as it's defined on real numbers. So, right. Good. Same is true of cosine of z equals 0, if and only if z is pi over 2 plus k pi. Okay. Right, so of course I kind of alluded to this already, but find other trig functions the usual way. Right? So that is to say, okay, so now I guess it's worth pointing out these have poles at pi over 2 plus k times pi. And likewise, poles at k pi analytic elsewhere. And same here. Okay, so the only reason I point that out is because, well, I want us to be confused, of course. Poles occur for functions other than rational functions, right? And when we do trigonometric integrals in the complex sense, this information will be important to us. It's hard to see right now, but recording of the zeros and poles of an arbitrary complex function actually give us all the information we need to integrate it over a given domain. Okay?
Is that because they're satisfied with plus 3?
Not exactly. That's not exactly on target. It's because we can decompose a function to parts where it is analytic away from a pole and just consider that in some part of the domain, and where it's analytic elsewhere, but possibly has a pole in a part that we integrated over there. We can separate it out if we know the poles. And that's a rough idea of what, but this is what we're going to be building to in the coming weeks. Of this beautiful theory of being able to compute definite integrals just by keeping track of the poles and the zeros of a function. Okay?
Just by looking ahead, when we compute definite integrals, we're talking about like sets, like not just over one pair, like not only over
That's right. We're talking about planar sets, not
just like a
intervals. Right. Exactly. That's why we spent the time we did talking about planar sets. Not only to put our formulation of differential calculus for complex functions on solid grounding, but that's especially important when we're talking about integration. Okay. Good. So, right. Here's a caution. We emphasize the similarities between complex and real trig functions. since formally, sorry, they are formally they're quite similar. What do I mean by formally? I mean they satisfy the same differential relationships. We can derive just symbolically the same identities in many cases. But as functions, they behave quite differently. But as functions, they behave very differently. Yeah, so for example, the absolute value of cosine of x is less than or equal to 1 for all real x, right? However, if we take, I should say, but, if we take the modulus of cosine of a purely imaginary number, I, y, then we're equal to the modulus, or really I should say, the absolute value of e to the negative y plus e to the y divided by 2 is unbounded. And in fact is never less than 1. Okay? So, well, okay, one thing you can say here, just because this came up in class, Joseph's comment, this is actually a hyperbolic cosine of y, right? Okay, so it makes sense that this is unbounded, right? Because what is hyperbolic cosine? It's if you draw a ray from the origin to a point on the unit hyperbola, you get the hyperbolic cosine is the x-coordinate of that. Is everybody, is it, I didn't want to talk about this yet, but you know, it is related here. Are we somewhat familiar with hyperbolic trig functions?
I've never actually gone over them formally, but I have like a vague understanding.
Okay.
Just use them in physics basically to simplify an ugly exponential.
Okay, right, so to do something like this.
Yeah.
Okay.
Just shorthand.
But it makes sense that the hyperbolic cosine is not bounded, right?
Yeah.
Because, you know, the hyperbola keeps getting larger and larger. So you as you draw, whereas like, as opposed to regular trig functions, you're looking at the unit circle, right? You're drawing a vector, an arrow from the origin to a point on the unit circle. So the hyperbolic trig functions are you're drawing a vector from the origin to some point on the unit hyperbola. Right? So as the hyperbola grows, your triangle becomes bigger and bigger and bigger. Whereas if you're drawing a point on the unit circle, you're bound by 1. Right? That would be this case. Okay? Yeah.
Oh, just a quick question. So for the modulus of cosine Iy, we could just do like from Calc 1 to differentiate the e to the negative y plus e to the y over 2 set equal to 0 and find the critical values, and then find out that it's never less than 1. Do that. Because it maxes out, or it minimizes at 1.
Yeah, you could do that if you wanted to, sure. But you could also just look at the hyperbola, right? You know, you're not going to get any shorter than 1. That's the the unit hyperbola is this thing, right? So as I draw points here, I'll never get shorter than 1, right? I'll come down here, 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 and further out. But yeah, you could differentiate if you want.
Does that type of method of differentiating, is that equal to 0, produce critical values for complex functions?
Yeah, critical value applies for any type of differentiation that is consistent with real differentiation, which is the case here, right?
So like, I'm not sure if I'll do it in class, but like if we could find critical values of complex valued functions and find like minimums and maximums of them?
Yeah, so that can be done.
Isn't there no ordering of complex numbers, so if we
Oh,
find a maximum?
Right, so you have to ask the question more related to a modulus, or, we're looking at, essentially, if we disregard the multiplicative structure, we're looking for a 2-vector, right? And so how do you classify critical points, right? You don't have the same notion of maximum and minimum, that's true, but there is a related notion having to do with the eigenvalues of the Jacobian. I don't know if that means anything, anybody, but yeah, there are things you can say. Let me just leave it at that. But yeah, good observation that, yeah, of course, maximum and minimum aren't the right terms to use for what a complex valued function attains, but you can classify its critical points, and that does have some kind of meaning. Okay. Good. All right. So, all right. What if we want to? We already kind of discussed this. What do we do when we want to invert a function which is not one-to-one? Okay, we talked about how you can invert. You can always invert an injective function, but what if we take a function which is not injective and we want to invert it? Well, that's where this notion of multiple valued function enters the picture, right? And we've already seen some of these constructions. It was in the first week, right? We talked about choosing a principal value for the argument and making a branch cut to well, really what we're doing is realizing that this argument function has some type of periodic behavior. So we were able to choose some region in which it's one-to-one. Or rather, where it attains only a single value for each input. Okay, so, right. So, now what we want to do is, consider again e to the z, and try to invert it. Okay, obviously this isn't necessarily well-founded because of what I just said, right? Inversion of a function really depends on it being one-to-one. But let's see what we can deduce. Let's let w equal to log of z if z is equal to e to the w. This is my definition, quote unquote. Okay? I'm just going to start with this and see what kind of formulae I can produce for the real and imaginary components of w. See what I can say. Okay? exponential function is never zero, we assume z is not equal to 0 in this definition. Okay? Let's let w, as we somewhat commonly do, be equal to u plus I times v. And we'll choose to take the polar representation of z, right? Which we'll take to be r times e to the I theta. Okay? Then what do we have? E equal e to the w implies that we're really looking at r times e to the I theta is equal to e to the u plus iv, or in other words, e to the u times e to the iv. And the modulus of both sides gives that r is equal to e to the u, right? Which in turn, remember, we're trying to get a handle now on the components of w. So now I just have an equation in real numbers, r and u, right? So now I'll say that this component u of w is equal to log of r. Okay, so notice here, I'm making a definition of a complex log function. I use the lowercase l. Okay, I use this capital L for now to mean the natural logarithm of a real number. Okay, I'm going to refrain from using ln because the textbook does. Okay. So there we go, we have this completely pinned down, right? We know everything about the real logarithm function, the natural logarithm function for real numbers. So we have one component of w down, okay? Now, what do we do about the remaining terms of our equation? E to the I theta is equal to e to the I times v, right? Which implies that v is equal to the argument of z. An infinite value function, just like we discussed previously in the beginning of the term. Okay, so if we have a complex number z which is not equal to 0, then log z is the infinite set of values the natural log of the real number, the modulus of z, plus I times the lowercase arg of z, or if you like, the natural log of the modulus of z plus I times the principal value of the argument of z plus I times 2k pi. Okay, in C, just in case we got the distinction between lower and uppercase R. Okay, so I want to point out that at this stage, the usual identities for the real natural logarithm function, or any real logarithm function of any base, but we'll mainly be concerned with e here, of course. The usual identities hold with the appropriate modifications for this infinite valuedness. Okay? Okay, so firstly, we have that z is equal to e to the log of z, right? This is unique, right? Because any of the args, any of the values of lowercase r of z I choose for this will give me the same thing for e raised to that, right? Because I could just separate the plus 2k pi out and get a 1. Yeah. Okay. But remember, the usual property of an inverse function is that if you compose a function with this inverse, or the inverse with the original function, you get the same answer back. But that's not the case here, right? If we take log of e to the z, what do we get? I get z plus 2k pi I, again, for k an integer. Okay, so up to this integer multiple of 2 pi I, it's the same thing, right? It's the same as the usual inverse function identities, up to this integer multiple of 2 pi I. Okay, so log z1, z2 is equal to log of z1 plus log of z2. Okay, 3 log of z1, z2 is equal to log of z1 minus log of z2. Okay, now there's 3 quantities here. Or rather, I should say, we're applying the function lowercase log 3 times. And each time it's infinitely valued. What do I even mean by writing this equality?
Is that within each fundamental, what do they call fundamental regions?
Well, now remember, the fundamental regions were defined for e to the z, a periodic function. I haven't yet verified that log is a periodic function, or that it has fundamental regions. What I mean by this, there are three quantities here. If any two of them are specified, let's say I specify what particular log of z1 I meant, and what particular log of z2 I meant. What I mean is that one of the infinitely many values that log of z1 times z2 takes will satisfy this equation. If I specify any two of these three values, the remaining one will assume one of its infinite values will make this a true equation, is what I mean by this. Okay? There's a homework, an exercise in the textbook that illustrates when this fails, when we choose a principal value for log. Okay? So I'm looking forward to what you think about that. But suffice it to say, for lowercase log, where these assume infinitely many values, if any two of those values are specified, let's say I specify the particular log of z1 times z2 and the particular log of z2, then one of the infinitely many values that log of z1 takes will make this equation true. Okay? All right. So, it's nice that these identities hold, given the correct interpretation, but just as when we dealt with the argument of a complex number, we don't want to carry all this ambiguity with us all the time. So we're going to have to do some work to eliminate the ambiguity. Right? Okay. I mean, basically, what we'll usually do is the obvious thing. We'll say that the principal value of lowercase log of z is just defined by the principal value of r. Okay? So now, I'll write capital log of z for the principal value is equal to the usual real logarithm of the modulus of z plus I times capital R of z. This is the principal value of log of z. Okay? So, what this means this function, this single valued function, log of z, discontinuities of argz, capital RZ. Where is argz discontinuous? Let me ask a simpler question. What is the range of principal values that arg takes?
It goes from negative pi up to including pi.
Yeah, exactly.
Does not include negative pi.
Right, so call capital R takes values and negative pi to pi. That is to say, when we encounter the negative real axis, the arg is discontinuous. It's continuous from, but not including, negative pi up until you get around to pi, i.e. the negative real axis. If you want to continue rotating around the unit circle, you're discontinuous when you pass the negative real axis. You go back to negative pi. Whereas if you were continuous, you would go to pi plus 0.001, or something small, right? As soon as you cross. But instead, no, you go straight back to something just beyond negative pi. Okay? So, right. How much time do we have left? Okay, enough to state this theorem, and then we'll prove it on Friday. So discontinuous on negative real axis. And so is log. So is log z. Okay, so it would be ideal if the inverse of e to the z, which is an entire function, was also entire. Well, we can't have that. It's discontinuous along, at least the principal value is discontinuous along the negative real axis. However, it's continuous everywhere else in the plane. And in fact, log z, the principal value, is analytic in a domain which we'll call D star, and the derivative is just 1 over z. Here's a picture of D star. Taking this negative real axis out. This is D star. The plane minus this negative real axis. So the principal value of log z is analytic everywhere except for negative real numbers. Which is kind of like the opposite thing that we were saying for cosine. right? Or there's a couple opposites going on, right? We said that the only places where sine was 0 in the complex plane, once we extended it, were the real values. Now we're saying the only places log of z is not differentiable are the only places where it's not defined for real numbers. The negative real numbers. And 0. Sorry, I should say the non-positive real numbers is where is what's excluded from D star. Okay? So, right. It may not seem like it now, but the exclusion of this branch is going to be really important to us for a lot of applications. Again, when we start to talk about integration, which we'll do shortly after we prove this theorem and do a couple examples related to it. Okay, so yeah, I'm going to send out the problem set in a little bit, and then don't forget I said I'll release some review material or practice questions, something for the exam next Friday. Yeah, oh, don't forget, if you did that extra credit thing, I'll take your work before you go. Or you can just send it to me on Canvas or over email, since it's not really an official assignment. Anyway, you guys give me fun.
And when's the problem set due then? Before Tuesday next week?
It'll be due on Tuesday.
Okay.
Yeah.
So would D star be C minus or C cut?
Sorry, say that again?
Would D star be C cut the set of all numbers with real value?
Yeah, that's exactly right. I'm just
less than 0 and
excluding,
then
I'm just excluding this entire ray
yeah, and then
that stems from here.
imaginary value 0.
Then that's what?
So it'd be the real values that are negative and the imaginary values are not 0. Oh, sorry, are 0. Right? It would be.
I didn't hear what you said about measure. What was that?
Sorry. Wouldn't it just be this? It would just be.
Yeah, that's a fine way to specify that. You know, there are many ways to say, but that's a fine way, sure.
Thank you.
Yep.
Have a good one.
You too.